Hello and welcome to this video. Today I want to talk about a fundamental shift in how we approach solar energy. When we think about the future of photovoltaics, the conversation usually revolves around new materials. So what if the key to breaking efficiency barriers isn't just about the what, but the how? In the framework of SHERPA project, we are moving beyond planar constraints to explore how laser-defined microstructuring can unlock the true potential of perovskite solar cells under high irradiance conditions. So be with me to see this story. Here we see the core industrial problem with conventional planar perovskite solar cells. As the light intensity increases, the efficiency rapidly collapses. As you can see from this diagram, this graph clearly shows the dramatic PC drop under high irradiance conditions. This happens because several physical limitations start to dominate simultaneously. But why? First, the fill factor drops due to increased recombination and series resistance. Second, thermal hotspots appear, accelerating degradation and instability of the solar cell. And third, large area charge transport become inefficient under concentrated illumination. The key message is this. Planar perovskite solar cells were never truly designed for high flux operation. And this is exactly where geometry becomes a powerful engineering tool. Microstructuring can be used as a design tool. But how? Instead of treating the solar cell as one large continuous device, we design it as an array of engineered micro cells. Look at this. You can see how laser-defined patterning divided the perovskite structure into isolated micro sections. This geometric segmentation is not just fabrication. It is physical engineering, which by controlling the geometry, we improve three critical mechanisms simultaneously. Better light distribution, reduced thermal accumulation, and shorter carrier transport paths. The layered schematic also highlighted the full device architecture from the substrate up to encapsulating layer. In other words, microstructuring transforms a passive planar device into a controllable high-performance system. Here, the key parameter, which is the pitch geometry, is very important. What does it mean? It means the space between neighboring micro cells. Here you can see the narrow pitch design. In this configuration, the cells are tightly packed. This increases optical crosstalk, thermal accumulation, and electrical interference under concentrated light. In contrast, on the right, you can see wide pitch. In this design, What can be provided is better optical confinement, improved heat dissipation, and a stronger electrical isolation. So the geometry itself starts controlling the optical, thermal, and electrical behavior of the device. The important idea is that the optimal pitch is not random. It is a balance between light concentration, thermal management, and efficient charge collection. Here we are talking about passive cooling via geometry. Thermal management becomes one of the biggest challenges under concentrated illumination. In a conventional planar solar cells that you can see here, heat becomes trapped inside the device. The limited surface area and restricted escape paths lead to thermal accumulation, higher recombination losses, and a rapid drop in fill factor. But look at the right. In the microstructure architecture, geometry itself assists cooling the system. The separated microcells create more open pathways for heat dissipation and increase the effective cooling surface area. As these blue arrows illustrate, heat can escape much more efficiently from the structure than the conventional planar solar cell. This reduces thermally activated losses and help stabilize device performance under high irradiance. So here, the geometry is not only shaping optics and electronics, it is also becoming a thermodynamic advantage. So what is the power of micro-optics? Optical concentration is not only about increasing light intensity, it is about controlling where the light goes. Here you can see a conventional macro-optics approach using large bulky lens. Although it concentrates light, the illumination becomes non-uniform, creating hotspots, spillover losses, and inefficient confinement. In contrast, as you can see on the right, the micro-optics architecture uses an array of microlens aligned directly with microcells. Each lens delivers light precisely onto its dedicated active area. This produces a much more uniform optical distribution while also reducing optical losses and system size. So instead of one large optical element, we can use arrays of microlens which distributes the concentration process across many engineered optical channels. This result is simple: more precise light delivery, lower losses, and higher efficiency under concentrated illumination. So what is the real challenge under concentrated illumination? It is not achieving a high peak efficiency once it is maintaining a stable fill factor as irradiance increases. In the center graph, the cyan curves represent our microstructure architecture. It is not a real graph, but it can show its properties. Even as light increases, the density of the light rises, the JV profile remains stable and well-shaped. It means that the fill factor is preserved. But for the conventional planar device, which is shown in purple, the curve actually progressively collapses under higher irradiance. This is mainly caused by thermal stress, transport losses, and increased recombination. The operating window comparison on the right actually summarizes the difference, which is very clear. The microstructure architecture, as I said, this is not a real JV, but it follows actually this manner and this trend. This maintains a wider and more stable operating regime, while the planar reference rapidly loses its stability. So the key advantage here is not only the efficiency, it is operational robustness under extreme optical conditions. So how to solve the opto-thermo-electrical puzzle? We should know that high irradiance performance cannot be solved by optics alone, thermodynamics alone, or electronics alone. It only works when all three domains are engineered together. This slide summarizes the complete strategy that at the top you can see the optical system, which uses micro-lens array to precisely distribute and confine light onto the active regions. The thermal domain manages heat through passive cooling pathways enabled by geometry. This reduces operating temperatures and minimizes thermally activated losses. And the electrical architectures improve charge collection through shorter transport paths and reduce recombination. At the center, all three mechanisms converge into one goal: a stable, high irradiance efficiency. So the key idea is that performance does not come from one optimization alone. It emerges from the synergy between optics, thermodynamics, and electronics. Here we move from efficiency to stability. Because for perovskite devices, surviving under stress is just as important as achieving high performance. Here you can see the microstructure device operating under intense concentrated illumination. Normally, this level of irradiance creates severe thermal hotspots and accelerates degradation. But as our test results shows, our architecture changed this behavior. The first key advantage is lower local temperature. By improving passive heat dissipation, we reduce hotspots formation and slow degradation kinetics. Second, we preserve phase stability. Lower thermal stress helps prevent phase transitions and ion migration inside the perovskite layer. And finally, this leads to longer operational lifetime while maintaining a stable fill factor and power conversion efficiency over the time. So the main message of this slide is simple. Stability is not accidental. It is engineered through geometry, thermal management, and control light. Finally, beyond the physics and engineering, we also need to think about economics. Because a solar technology only matters if it can become scalable and affordable. You can see the first advantage of micro-concentration solar cells, which is using less active material by generating more power. By concentrating and managing light, more efficiency will be obtained and the device extracts higher performance with less perovskite material. The second point is manufacturing scalability. The image here actually shows the laser-based patterning, which enables fast, maskless, and highly reproducible fabrication of microstructure device. That makes large-scale production much more realistic. And now here you can see the trend as efficiency increases, the cost per watt decreases. And our goal is to push the device toward the optimal operation region where performance and economic values meet. So the main idea is not only achieving higher efficiency, but also achieving it in a way that reduces cost, simplifies manufacturing, and increases practical impact. In this slide, you can see the roadmap that how we can move from a laboratory concept to the real world deployment. You can see the vision large scale solar system using microstructured perovskite technology under real outdoor condition. The goal is not only high efficiency, but also reliability and scalability. And also there are three next major steps that has a space to work actually, which are the real world stability testing. The microstructured solar cell, microconcentrated solar cell need to be validated for long-term operational working under outdoor environment, temperature variations, and continuous irradiance stress. Second is the actually integration with solar tracking systems. Because concentrated light system perform best when optical alignment is optimized dynamically throughout the day. And a third, scalable manufacturing. Laser-based patterning gives us a pathway toward fast, reproducible, and cost-effective mass production. So these are the main areas that have a space to be worked on in the future. Also here you can see the potential application spaces for micro-concentrated solar cells from a smart energy system and solar farms to a portable electronics and IoT device. And finally, we can say that here it is the summarizing of the roadmap. Which is validation, integration, and scaling up and deploying. So the key message here is that this is not only a material project, material changing project. It is a platform for translating microstructured photovoltaics into practical energy technologies. Finally, I would like to emphasize and conclude with the broader vision behind this work. This project was not only about improving perovskite solar cells, it is about engineering a new way to combine optics, thermodynamics, and electronics into one integrated high-performance platform. Throughout this presentation, the key message has been consistent. Geometry is not just a structural parameter. It becomes a tool for controlling light, heat, and charge transport simultaneously. And by doing that, we can move beyond the limitations of conventional planar perovskite device toward stable, scalable, and high irradiance photovoltaics. Thank you for your attention. You can scan this QR to see more about our project, and also you can be in contact with me through this email, and feel free to leave your comments and any idea that you think about this project. Thanks and have a nice time.